And we saw some example also last lecture, right? And let's see, yeah, we saw some example. What is the last one? Okay, I didn't get any information from the date of exam. I don't know yet. Okay, from the relation chapter, we will write closure properties and closure properties. For closure properties, let's say we have, a set A and the collection of all relations relations on A, let P be a property of such relation. Such being symmetric or being transitive. A relation with property P will be called a P relation. The P closure of an arbitrary relation R on A written PR, P of R is a P relation such that R is a subset of PR. There's the relation R and subset of PR, and it is also subset of S. For every P relation, S containing R, and we will write reflexive symmetric reflexive R, symmetric R, and transitive R. For reflexive, symmetric, and transitive, closure of R. So generally, P of R need not exist, and we can write P of R is equal. Okay, end of the lecture, I will talk about the midterm exam. Actually, I'm planning, take-home exam. As a homework, I will send you homework from the UBIS in, some duration, maybe 2 hours, something, and you will solve your question, then you will upload the system as a UBIS. So this is the way you will take kind of, exam from the UBIS. There is a restriction for time. You will solve and upload your question. That's it. Okay, let's look at the example. Okay, example. So consider, but I don't know how many questions exactly, because I didn't prepare any question for the exam. Maybe 3, 4, maybe 5 questions. So we have set A. Until today's end of the lecture, what we talk about, all title or topics or example included by the exam. Okay, this is the example. There is the set A and relation as a relation pairs as a 1, 1, 1, 2, 1, 3, 3, 3. And there is the relation pairs as a 1, 1, 1, 2, 2, 1, 2, 2, and 3, 3. And there is the T 1, 1, 1, 2 as a T relation pairs, and 2, 2, 2, 3. And there is also, empty relation, and there is the universal relation set as a product A. Okay, question. Determine whether or not each of the above relations on A is A as a case A reflexive, and case B as a symmetric, and case C is a transitive, and case D as a antisymmetric. Antisymmetric. And solution as a solution. Can you see the page? This kind of yes, you can see the page. Okay, and solution case A, R is okay. Case A, R is not reflexive because 2 is the member A, but 2, 2 pairs is not inside of the relation R. T is not also, T relation pairs is not also reflexive. And there is the 1, 1 inside of the T pairs, and 2, 2. But as you see, there's the, and 3 is a member of A. And when we look at the pairs of T, there is no 3, 3 in that relation pairs. And what else? And how about S? We have 1, 1 inside of the S, and we have 2, 2 and 3, 3. So S is reflexive, right? And I won't write any reason or explanation for that pair set. And S is reflexive. And what is the next? Empty set is not reflexive, of course, right? Not reflexive. And how about universal set? It is also reflexive, right? As a product A, it is the plural, right? Are reflexive. Okay. Question? Yes, no. And case B, this was the case A. And I need some paper. Okay, one. Can we write here as a case B? Okay, let's try the case B right here. And case B, R is the pair set, and it is not, symmetric. R is not symmetric because there is a pairs as a 1 2 inside of the relations R, but we don't have 2 1 in our pair set R. And similarly, T is also not symmetric. And we can use the same reason. There is the 1 2, but not 2 1 inside of two that relation pairs, right? Okay, let's write the same pair 1 2 as a T, but there is no 2 1. And is there any more? Yeah, there is a 2 3 also, and R also 1 2. You don't have to check for all pairs. If you find one, that's it. One is given the reason that is enough. You don't have to write for all. And T, so we can say S. Okay, let's look at 1 1 1 2 2 1 2 2 3 3. S is symmetric. So I don't write any explanation because I have 1 1 1 1. Again, you can use that pair, and it is gonna be symmetric. 1 2, also there is a 2 1, and 2 2 3 3. Both for that pairs, both properties as a reflexive and symmetric is working. And also you remember the reason for empty set and universal set and universal set, those also are symmetric. Okay, this is case B. And case C as a transitive, T is case C. T is not transitive. Why? We have, okay, as a T, why we start from the T? Okay, this is the explanation. And T we have, 1 2, and starting with the 2 is a 2 3, right? If you look at 1 2 and starting with the 2 2, I mean the first member of the pairs is a 2, you know, there is the 1, 2, and 1, 2 is a pair member of that T relation, and 1, 2, and 2, 3. When I check that two pairs as a, you know, 1, 2, 2, 3, I need to member the pairs 1, 3, but there is no 1, 3. That's why I'm gonna use that, you know, condition as a T is not transitive. You know, reason is 1, 2, and 2, 3 belong to T, but I don't have the 1, 3 in that pair set. So if I consider that properties, I mean the transitive, you know, for R, you know, 1, 1 is gonna be also reflexive, you know, symmetric, and 1, 1, 1, 2, and there is 1, 2, it is working again, and I have, you know, some freezing something on my screen. I'm waiting my cam reflection. Okay, now it is okay. You know, 1, 1, 1, 2, and 1, 2. This is the, you know, transitive, and 1, 1, 1, 1, 3, 1, 3. It is also working, and for whole, you know, pairs R is and transitive, and S. Let's look at the S. 1, 1. 1, 2, 1, 2, 1, 2, 2, 1, 1, 1. It is a member again, and 1, 2, 2, 2, 1, 1, and 3, 3. S is also, you know, transitive, S, R, S, and empty set, and universal set are transitive. And next one is a D. You know, S is not antisymmetric. Why? Because okay, 1 is not is equal to 2, and 1, 2, 2, 1, 2, 1, both belong to S. That is the reason, you know, for that pair 1, 2, 2, 1, and they are not is equal to each other as a 1, 2, and you know, 1, 2, 2, 1. It is the member of the S relation pairs, and we will say S is the R is the transitive. R is the transitive, Zainab. How you get the meaning, right? Because I explained the R. You know, there is the 1, 1, 1, 2. If you check the, you know, starting and ending, 1, 2 is a member of that pairs, and ending with the 2, but there is no starting with the 2. 1, 3, you know, 3 is ending with that pairs ending with the 3 and starting with the 3, 3, 3, 1, 3 is again the member of the R. So I will say R is the transitive. And antisymmetric, so this is the reason for S, and there is also a product A is not antisymmetric, antisymmetric, rest of the relations are antisymmetric. Okay, we saw as a closure properties example, and now we can start the new chapter. Please get said. Okay, 1, 2. So what was the antisymmetric properties? Do you remember? Okay, I will write the theorem. A relation because S is the symmetric. This is enough, or should I write to theorem or definition? Okay. Okay, thank you. Because it is gonna take some time, and as I remember, we saw for the empty set, there is the reason. Okay, for the symmetry, if you have or transitive. Okay, let's check the transitive. If you have 1, 2, and ending with the 2, starting with the 2, that the pair. So for that transitive, you have to remember as a pair 1, 3. But empty set there is no any pair. So it is going to work for the transitive. So this is a little bit strange, Salman, but you will keep the information like that in your mind. Otherwise, it is gonna be hard. Okay. If you have 1, 2, ending, just think about that set, pair set RST, let's say as a Q set. Okay, let's say as a Q set, I mean relation pair. There is the 1, 2, but there is no 2, 1, right? In that pair. I mean the relations. There is no 2, 1. So this is also transitive. Yes. It is not symmetric. It means it is gonna be antisymmetric. Okay, I will start the new chapter as a functions. Okay, you're welcome, Salman. Okay, function and algorithms. It is gonna be our new chapter, functions and algorithms. Functions. So this is also, some basic theorems, but maybe we will do something more, and we define relation from, as a chapter 1 we saw the set theory, and chapter 2 and we talk about the relations of the set, and in that chapter we will talk about the functions and algorithms. As a chapter 3, functions. Okay, let's write something. Is the terms like map, also mapping. Sometimes you can look like that side as a mapping, or transformation. Transformation from somewhere else to somewhere. And you can use some many other mean or word, the same, same thing. But generally for function, as a definition, if you want to define, okay, let's say, suppose that to each element of a set A, we assign a unique element of a set B. So unique, we have to quotation mark for that word, is a unique. And what we said, suppose that each element of a set A, we assign a unique element of a set B. Set B, the collection of such assignment is called function. A function from A into B. So, you can think about the relation. Relation is also similar, right? And there is a set A and there is a set B. If we define something from the member of the any element of set A from the member of the any element of the set B, we were saying for that, that assignment as a relation, but here we did something as a different, as a unique, as a specified word for that relation, and we said as a unique, and the set A is called the domain of the function, and the set B is called the target set or codomain. Okay, for the definition of the or notation of the function, we can write as a f as a function from A to B, from set A to set B, and we can say for if A is a member of set A, and then we can write as a f in parentheses A. So it means we can read that one, you know, that one as a f of A, right? F of A, and denotes again the same word, the unique element of B, right? To A, it is called the image. It is called, B side is gonna be image set, F, and or we can say for the image side, or the value from the set B of f at A. So as an example, you can say, and I'm sure you know, there's the f of x, and you can represent to that system as a, you know, x square as a function, or you can say x goes to, you know, x square as a function definition, or you can say, you know, there's the y as an image set, and there's the you know, equalities left side as a image set, and right side as a domain as a x square. So also you can say x is variable and f denotes the function, of course, and also x is, you can say as a more, x is independent variable, and as other side y is dependent variable for that function representation. An example. Okay, we have as a Venn diagram sets as a and B. Okay, this is the A and this is the B. So for that, sets, we have as a function from like A to S as a unique, right? There is no any image from the set here. A has only S and B has a U and C has a image are in set B and D can go to S. So write the functions equalities. Okay, case A. So f A is equal what? Fa, there is the defined function from A to B. So we can say f, define the function from A to B. So fa is equal S, right? Yes, thank you, Emre. And B, fb is equal as a U and C as a FC is equal R and D as a FD is equal S. And in that image set, if you care about that function, there is no any connection with the set A of T as a image image set, but it is not taking any member from set A. And function and relations as a title. So as a functions as relation, there is the some definition. There is another point of view from which functions may be considered First of all, every function from A to B gives rise to a relation from A to B called the graph of the F and defined by graph of F there is the AB pair in that function. A is a member of set A and B is equal FA. And if there is the two function from A to B as a function f, and there is the function g from again A to B as a two function, are defined to be equal, then written f is equal g if fa is equal ga for every element of A member set A. Then you can say, both function have the same graph. And as a definition, a function as a f function from A to B is a relation from A to B such that each A is a member of set A belongs to a unique ordered pair AB in F. And these are the definition. And let's check. Okay, let's write the example. Example, this is page 3. Example. Okay, for that one, that example, we have set A and set B, and there is the function or those set, and A goes to S, and C or B goes to U, and C R, and D again S for A and B. Okay, define function as a f from A to B. Write the graph of f so graph of f is what? A goes to S and B goes to U and C R and D S. I think now, can you see the shared page? Okay, do you hear me? I think we lost the connection. Okay, do you hear me? Now that is okay. I'm in the shared screen. Okay, now is okay. Do you think that we can we do a break, like the 10 minutes, then we continue the functions? Do you hear me? How about break? Do you want to do break? Screen is frozen. No, screen is, I think, okay. It is working. I mean streaming. Okay, 10 minutes break. Now again something happening. Dear friend, do you hear me? Okay, composition function. Okay, again, like the composition of relation, we will write the similar something for the similar theorem for the function. Let's say we have functions f from a to b, and there is the g as a function from b to c. Okay, there's the domain and codomain. Okay, that's fine. Or the codomain of f is the domain G, domain G, then we can talk about the new function from A to C, right? From A to C. So, which is called the composition of F and G, and written as a G of F, right? So, which is G of F as a composition function. A is equal to G f of A. So G of f of A. We will say there is the equalities. Okay, if again there is the two function. I'm sorry. There is the two set and function for that two set as a f a to b, and there is also f composition like the IA. How about now? Streaming is okay for the shared screen. Can you see the Halil, can you see the page? I mean my handwriting. Yeah, because of the internet. Buket, there is the book also you can follow, and I will share that note with you, and then you can repeat by yourself watching the movie of the lecture. So I'm really sorry, this is the online lecture. There is some advantage and disadvantage also. Okay, let's write that one. And there is the F composition IA. Let's say this is equal F. And there is also IB composition F is equal F. Then IA and IB are the identity functions on A and B as a respectively. Okay, there is some properties or kind of classification of the functions. Let's write these as a one-to-one, and onto and immutable functions. As a title, and let's write those as a step-by-step. A function, the first one. I hope connection is good right now. A function f defined from A to B is said to be one-to-one if different elements in the domain A have distinct images. So another way to say that one is that F is one-to-one. F is one-to-one, one-to-one. Okay. If fa, okay, let's write here, f of a is equal f a hat implies a is equal a hat. Sarah, what is your question? The second one, but on my, I'm looking also, checking the streaming of my page. It is working right now properly. Okay, let's reduce to some percentage of stream. I hope this is going to help to connection of our streaming of movie. A function as the second one, f, again a to b is said to be onto, to be an onto function if each element of B is the image of some element of A. Another way to explain that condition, f A to B, f A to B is onto if the image of F is the entire codomain like if f of A is equal B. In such case, we say that f is a function from A onto B that f maps A onto B. And next one is the immutable function. A to B is immutable if it is inverse relation f minus 1 is a function, must be a function, from B to A in generally, of course, you will accept that one. The inverse relation like the F inverse may not be a function. This is the reason. Otherwise, we will say this is the immutable. Okay. Example. We have A, B, C, D, E sets. We have sets A, which are A, B, C, D, and E. There is function. There is functions given on Venn diagrams. So let's draw Venn diagrams as a set A and B, C, D, and E. So we have A, B, C in set A, and there is the 1, 2, 3, and 4 in set B. R, S, T, U, R, S, T, U in set C, and there is the V and W in set D, and X, Y, Z as the last set as a E, and there is the function from A to B as a function notation as a F1, and A goes to 4 in that function, and B goes to 1, and C goes to 2. This is the F1. F1 is the function from A to B. And there is the function as a F2 between, and I mean from B to C, and 1 goes to R, and 2 goes to T, and 3 goes to U, and 4 goes to S. Yes, there is the S, and F2 is a function from B to C, and there is C to D, R goes to V, and S goes to W, and T goes to W also, and U goes to E. And this is the F3. F3 is a function from C to D. And last one is F4. F4. And there is the V to Z and W to Z. This is the F4. D to E. Okay, what is the question? Okay, define the functions. Okay, define, this is our question. Define the functions one-to-one, one-to-one, onto, and invertible. So this is our question. So start with the F1. F1 is one-to-one, right? What do you think? One-to-one, because the first one, you put it the star as a solution. Okay, F1 is one-to-one. Yes, Holly. Today's, uh, lectures is gonna be inside of the midterm. There is no so much information. I mean, strange or detailed information. This is a general math theory, like the set theory and relations theory and functions. We couldn't come to some specified titles actually. Okay, F is the one-to-one because we were writing that one. No elements of B is the image of more than one element of A. So we are looking for again the function F1. So I didn't set any date and time because department will decide the exam schedule. They will announce it. Then I will put your exam in that planned duration or planned date and time. So F1 is one-to-one because each of the element of B taking the one element from set A. Zeynep, I don't know that one. If I have to plan a date, I will announce today, okay? Okay, I got that one, Emre. I told, department will plan the schedule of the exam. So they don't remind me anything about that. Just they give me information about what I'm gonna do as an online exam or, like the regular take-home exam. I told them I'm planning as a, regular take-home exam using the UBIS. That's it. They didn't me any information which I do plan for date or something. Okay, F1 is one-to-one because one set A member is coming to one element in set B, and next one F2 also one-to-one. F2 is one-to-one. Right? And F2 also onto function, right? Because any question? No, okay. Because every element of C is the image under F2. Okay, F2 is one-to-one, also F2 is onto function. And what else? F3 is one-to-one? No, F3 is not one-to-one because an element of C, okay, let's write on image set B element V has two domain relation from set C. No, I write something is wrong. This is the D. This is the D from set C. dv in the f3, and f3 is onto. Yes, it is also onto. f3 is onto function because what or why? Because they are covering the whole member set B, right? Since every element of D is the image under F3. And what else? F3 and F4, it is not 1 to 1, right? It is not onto, right? I mean F4. So you are writing for correction what I wrote, or just you are repeating the same information? Yeah, you are writing as a F4, Emre. I got it. And I'm reading what you write. And we said F1 is not on to, right? F4 you are writing F4, and what do you mean for? Okay, F4 is not on to. Okay, start with your explanation. Is not on to. How about 1 to 1 F4? Okay, is not. Is not 1 to 1. And you know, this is not synchronously. You are writing something, I'm thinking what I wrote. It is not working the same time. You are thinking something, I'm thinking different something. And F4 is the not onto, and not one-to-one, and what else? F1 is not onto, right? F1 is not onto because the tree is not covered by set A. Yeah, it is gonna be composition of function A to E. At that time, it is different story. Emre, F3 is not onto, and F3 is not one-to-one, and F3 is onto function. We mentioned that. How about F4 is not one-to-one, is not onto, and it is not also invertible, right? F4 is not onto, is not one-to-one, also is not what we said, invertible, because there is no unique member or image element for f of reverse of f of z. And is there any something more we have to talk about? And f3 is not invertible also. f3 is not invertible. Why? F3 is not invertible because W goes to two different image sets at that time. And F2, is it reversible? I mean, if we take the F2 as an inverse, it is going to be a function. Yes. F2 is going to be invertible. Also, you know, and F2 was also onto function. Because of that one-to-one onto function, also invertible. Zeynep said yes. I hope she said for that condition as a F2 is the invertible. How about F1? F1 is the invertible. Yes, this is also invertible, but not one-to-one. But it is also onto, I'm sorry, reverse of the F of 1. Okay, let's write the table. F1, F2, F3, F4. So please help me to fill that table. And we have one-to-one, one-to-one, and I have onto here, onto, and last one as a invertible or reverse f of f, invertible. Okay, let's fill together. Okay, make it here as a 2-piece and again and again. Okay, F1 is 1-to-1, right? Okay, I'll answer that one, Zainab. F1 is 1-to-1. How about F1 is onto or not? Okay, F1 not onto. Okay, how about invertible? Okay, Zainab is your time. Not invertible because we are not taking the for 3 on image set, right? Okay, not invertible. How about F2? F2 is 1-to-1. Yes, right? F2 1-to-1. How about onto? Yes, it is onto. If 1-to-1 and onto is working, so invertible also is working. And F3. How about F3? It is 1-to-1. No, it is not 1-to-1. How about onto? Yeah, it is covering the all member on the image set. How about invertible? It is not working 1-to-1, so it is not invertible. And F4, is it 1-to-1? No. Onto, no. Invertible, no. So this is easier, I think. Easier than that way, because we missed some of them, but we cover all properties of the or type of the function writing in that table. Any question? Any question? Okay, how about at 7? Can we do a lecture for today? Do you think that we should do lecture? We should do something more. We have some 1 hour at 7. Maybe we can solve some more examples. You know, that chapter is really important. This is the easiest or easier part. You know, second part, if you divide that chapter as a 2 part, first part is really easy and second part is little bit, you know, hard when you compare the first part. I see. Okay, okay. I won't do any extra hours for tonight. I mean that evening. I'm sorry, that evening lecture. So I will send you maybe study example from the solved example of your book, and can we discuss about the can we discuss about the our midterm time